Good morning, folks. A couple of real brief announcements before we get started. One, I am wrapping up the grading, finally, of your exam. I'm dreadfully sorry it is taking so long. With my last weekend being completely unable to do anything, I am very behind this week. But it is my hope that I'll be able to finish that up today. As soon as I am done with that, I'm going to be conferring with Dr. Tamaro about scales for each of the exam versions. And once all of that's done, it'll all be posted and you'll have your exam grades and you'll be ready for next week. Well, you'll be ready maybe to think about the exam grade for next week. Whether or not you're ready for that exam is entirely up to us. It's how well we finish up this chapter, how well you are working through the material, and how we can work together if there are still any deficiencies. By this point, I think next week's exam, which will be on Wednesday, it'll be our last Wednesday exam, should, fingers crossed be, wait a minute, did I get that date right? I think I got that date right. I'll look that up as I'm rambling. It is my hope that by now we're at least familiar with the sort of general format, all of that stuff, and that we will be able to sort of focus primarily on the content. I have not yet uploaded the actual solutions, but I will be doing so today, along with the grading rubrics, so you'll know exactly how the things are being graded. That will hopefully tide you over if you are looking to go back over material from the previous exam. And yeah. So next week is, in fact, exam. Good. On Wednesday, yes, I was right. No problem. All right. With that said, I don't really have any other major announcements. Keep doing what you're doing. I'm going to be expanding my office hours slightly next week on Monday and Tuesday to give folks more of an opportunity to meet with me. I would normally do so today as well. However, I am just slammed and I want to make absolutely sure I get as much time to finish grading your exams as possible. So I will not be expanding office hours much today. But next week, Monday and Tuesday, I will plan to expand my office hours so you have additional time available to meet with me if you are worried about Exam 3 content. Otherwise, it's business as usual, and we are moving on to the last topic from Chapter 7, which is center of mass. Now, this part of the chapter is relevant to the fact that we talk a lot in this class about things moving places. Cars traveling, runners running, balls being thrown, projectiles being fired, all of this stuff, right? But we never actually talk about the fact that these things have size and shape. I am a person. You can hope, well, maybe I'm a robot, I don't know, but at least I look like a person from the point of view of you out there in digital internet land. And I am not a single thing. I've got arms, I've got a head, I've got a torso, legs that you never see. I have physical extent, I have shape. So if you talk about, say, my mass, call it 70 kilograms, and you talk about, well, it's maybe a little flattering, 75, let's call it. And you talk about the mass of me. Let's say I was doing a kinematics problem where I'm a runner and I'm applying a force and you have to figure out what my acceleration is. Like, great, I have a mass. But where is that mass? I am a physical body with a really complicated three-dimensional shape. Now, in really complicated physics, you can model things down to a detail. I can define mass throughout my body, and I can come up with the mathematics to do so. Unfortunately, in order to do that, we need calculus, and we're not doing that in this class. And it turns out also that that very complicated approach of distributing mass over a weirdly shaped body is broadly unnecessary for introductory physics. Instead, we talk about an object's center of mass. That is to say, the point that represents the centermost point of their mass distribution. It is the middle of the object. To that end, we can take extended objects like a person or a car or anything else, and we can condense that down to a point. Now, we are going to talk about center of mass today, and I'll walk off screen as you're looking at this slide here, and I'll give you some examples of what it looks like and what it means. Now, if I were to phrase it in the simplest manner, the center of mass of an object is the point at which that object would balance if you were to try to hold it up supporting just a single point. Now, this is very straightforward and very simple for objects that are very well behaved. Say, for example, this metal pole. I can just take my object, I slide my hands in, and at the point at which they meet, that is the point at where it will balance. And so, got it a little bit off there. This is this object's center of mass. Now, it's probably easy to understand for a really thin object like this, but it also works for, say, for example, if I were to have a little barbell where I were to have masses on either side. And if those masses were different, the center of mass won't always be in the actual literal middle of the object. I can give you another example of that. Here's a baseball bat. Definitely oblong shaped. So you'll note if I do that same experiment and I move my fingers together, the center of mass isn't actually in the middle of the object anymore. It is offset to the right. This end is more massive than this end, so the center of mass is shifted towards the more massive end of the object. But you don't have to stop there. We can even talk about the center of mass for really strangely shaped objects. Here is, well, this is objectively a yellow crowbar. My green screen seems to think that it's green, but that's okay, it's yellow. And I can do the same thing as well. I can just slide my hands in and note that even though this has a weird hook shape, the center of mass can still be found, and it is the point at which it balances. You know, this trick where I'm sliding my hands in to find it, that's a fun little piece of trivia you can use to impress your, let's say, really easily impressed friends. Because, you can do that for any given object. Even, for example, let's say I wanted to take a guitar and I wanted to find its center of mass. I could do that as well. And in fact, here we see, by sliding my hands together, the center of the mass of this guitar is somewhere right around here. And, of course, I don't want to break my guitar. But you can see I can balance it from this point without supporting the other end. So there you go. That's how we generally conceptualize what the center of mass is. If you've ever seen, say, figure skaters doing a routine in the Olympics, and you see one of the figure skaters lift the other one up, and the other one sort of splays out in a really impressive show of gymnastics and athleticism, that lower skater is almost assuredly supporting the suspended skater under their center of mass. Same thing is true in all sorts, if you palm and cheer, things like that, anytime there's stunts involved. Now, this idea works both for, yeah, don't worry, it's fine, it's back on the table, Joe. This works as well for extended bodies as it does for individual masses. So let's say I take these two objects with different mass and I connect them by a rod. Surely I can do my same little experiment here and I can find the center of mass and support it by that rod. But note, if this rod is very, very light, meaning its mass does not contribute to the problem here, I can define this point just as easily if those two masses were not connected to one another. And that's the sort of basis for where we're starting today. Now, we can calculate the coordinate of the center of mass using a couple of rules that are outlined in the text. So if, for example, I have these two masses on a horizontal line, I'm going to call that x, I can calculate the x coordinate of the center of mass based on the x coordinate of each of the individual masses and their actual masses themselves. This is the formula to do that. First, you calculate the total mass. You add up all the mass of all the objects you're trying to calculate. So let's say, for example, I had big mass 1, maybe a little mass 2, medium mass 3, big mass 4, and a small mass 5, I would just add all of those up. M tote is just M1 plus M2 plus M3, and so on and so forth until I add up all of my individual masses. Now, once I have the total mass, I take each object, I take its specific mass, divide it by the total, and I multiply that by the x coordinate of that object. I do the same thing for the second one. I do the same thing for the third one. And I do that for all of my objects. And then, as you can see here, I just add each one of those up. M1 over the total times x1, M2 over the total times x2, and so on and so on and so forth, until I get to the last one. N is just a number. It's the largest number you have in the sequence, so here it would be 5. So Mn over M total times the x coordinate of that nth mass. Now, this formula here, if that's the way you're comfortable doing it, great, do it that way. But we can actually express this in a more succinct manner. We write it in terms of a mathematical summation. That's what this big symbol looks like. This is the capital Greek letter sigma, and we read this as literally an instruction to perform the sum of things that look like this. So what I would do is for my variable I would plug in 1. I'd multiply m1 times x1, and then I'd go to the next I. From 1, I'd go to 2, and so on. Let me show you what that actually looks like. This sum for the variable I from 1 to n looks like I take my first value of I, and I multiply m times x. I then add to it because I'm doing a sum. My next I, which is 2. Then I add my next I, which is 3. Then I add my next I, which is 4. And I keep doing that for 5, 6, 7, 8, 9, 10, however many particles I have, until I get to my last particle, which I've indicated with the variable n. I then take this whole thing, put parentheses around it, and I divide the result by the total mass, which is what's being indicated in this mathematical summation right here. I'm going to pause because basically we've already done all of the hard stuff in this chapter is kind of on this slide, these two slides. And I'm going to pause here briefly. I'm going to take a sip of my coffee and give you a second to think about this. And I'd like to ask if there are any questions, because we're going to use this a couple of times, and then we're just going to see how it varies, and we're going to use it in the y direction, then we're going to use it to talk about velocity. So it's really important we're all comfortable with the basic premise of what I'm doing here. So I'm going to enjoy a nice relaxing sip of my coffee. And I'm going to let you ruminate on any questions you have, and I'll take about 10 seconds or so, and maybe I'll try to find another object that's oddly shaped to find the center of mass on while I'm waiting to see if you have any questions. I have 1,000,001 things in my basement, and none of them are particularly effective demonstration aids, I'm afraid. C'est la vie. If we had more time and I was in the university, we might actually have well thought out demonstrations that I could share with you. Unfortunately, in this COVID-19 induced virtual learning, we have to make do with whatever your professor finds in his basement, which is not much of use. Okay. I'm not seeing any questions in the chat. So I'll stall for a couple more minutes here, but I will take that to mean that everybody is on board with what we're doing. Now that we have our expression for how to find the x-coordinate, this cm means the x-coordinate of our center of mass in terms of this weighted sum, let's actually look at a couple of examples here. Now, when we're dealing with just two particles, that formula actually simplifies quite dramatically. This is not a new formula. This is no different. This is just what you get when you only have two masses and you plug it in, and I just plug in for the mass total. You might find this a useful shortcut for some homework problems, maybe not. But the one thing I want to mention for this particular version of the formula is if, and let's go ahead and get that back to red, if M1 is equal to M2, let's say I just call them M, you'll notice that this formula becomes, I can factor out an M, and in the bottom I get 2M. Those two masses cancel out, and I get that the center of mass for two equal mass objects is the two components added together divided by 2. What this is saying mathematically is exactly what we already observed with our nice regularly shaped object. For something that is regularly shaped, you can imagine this as having a dumbbell on one side and a dumbbell on the other side of equal mass. The center of mass will in fact be in the center of the object, just the average of those two positions. This is just a special case of this formula here. I know that a lot of you, you kind of struggle differentiating like what are the important equations here. This equation, and I'm gesturing to both of these because they are the same equation, this is the general solution. This is the one that's important. These are specific applications of that general formula that we use to draw conclusions about specific cases. All right, with that out of the way, let's actually do a real calculation here. We want to know, where is the center of the mass of the Earth-Moon system? The mass of the Earth and the mass of the Moon are given to us, and we are told what the average Earth-Moon distance is. It's worth noting that if you have a homework problem, you might not always be given these values. That's because they are available in the back of your book in the appendix. You can go into Sapling, go into your ebook, and from there, there's a section called back matter, which is all of the stuff that would normally appear at the back of the book. And in there are some appendices that include information like this. So things like the mass of the Earth, mass of the Sun, mass of the Moon, distances between them, those are all in there. And you'll find that that's going to be particularly useful in Chapter 10 a couple weeks from now. But for here, I've done the legwork for you. I've gone into the text and I've grabbed those values and I've written them down in the problem statement here. Now, the first thing you'll notice is the masses and distances are really, really big. Earth has a mass of roughly 6 times 10 to the 24. That is 10, and that's 1 with 24 zeros after it. That's a big number. The Moon is also a big number, 7 times 10 to the 22. But note that that is actually significantly smaller than the Earth. The Moon is, roughly speaking, 100 times less massive than the Earth. This means our system, which consists of the Earth and the Moon, is not equally balanced at all. We are also told that the average Earth-Moon distance, and let me actually write these down, 5.98 times 10 to the 24 kilograms. Here it's 7.35 times 10 to the 22 kilograms. And the distance between them, on average, is 3.84 times 10 to the 8th meters. Note that I say on average for a couple of reasons. One, the Moon's orbit is not exactly circular, so sometimes it's further away from the Earth and sometimes it's closer. Also there's small little perturbations that happen. It turns out the Moon's orbit is at an tilt to the sort of axis that the Earth's moving around, and all of these things complicate it a little bit. We just talk in terms of average distance to make that simpler. Now, first thing you'll notice is I give you a radial separation, not the x coordinates of these things. This is common. And whenever you are faced with a problem like that, where you are not explicitly given the x coordinates, it is up to you to first set your origin. And the easiest thing to do in cases like this is always to pick one object, doesn't matter which one, whichever one you want, and just say that that object is at x equals 0. This is related to our freedom to choose our coordinate axis. Remember, all throughout Chapter 6 with potential energy, all throughout Chapter 3 with projectile motion, or even in Chapter 5 with those inclined planes and friction. We were always free to choose our coordinate axis and to pick where x equals 0 is. We make use of that here. Because then, if that is 0, then the other coordinate is just 0 plus that radial distance, which would be 3.84 times 10 to the 8th. So now we actually do have coordinates. Now, we could use the simpler one down here, but I'm not going to bother. I'm actually going to do the full version just to make sure that we're really comfortable using it, just in case you get a problem on, say, a homework or an exam that's not a simple two-body system. And the first thing is always to find the total mass. Now, in this case, it's just 2, so we just add up those two numbers. 5.98 times 10 to the 24 plus 7.35 times 10 to the 22. And what I get is 6.0535 times 10 to the 24 kilograms. You'll note that it is only a little bit larger than Earth's mass. This makes sense. The moon is pretty small compared to Earth. You'll also note that I kept a lot of significant digits that are not going to be kept. This is related to a common problem I see on the homework where people round off their answers too early. While that is probably a reasonable thing to do most of the time, in this particular class, instead of focusing on how uncertainty propagates through these things, what we want to do instead is just be very careful, carry any digits through all the way to the end of the problem, and then do our rounding. This, strictly speaking, is probably not the most rigorous way of treating uncertainty, but nonetheless, it's good practice for making sure that Sapling doesn't yell at you for rounding your numbers off wrong. So I'm making this recommendation as a sort of pragmatic or practical suggestion. Now from here, we calculate the center of mass. It's 1 over m total times the sum from I equals 1 to, now we have to specify what n is, and that is just 2. N is how many objects are in your system that you're trying to calculate the center of mass of. Here we have 2 objects, so n is equal to 2. And that will be the sum of mi times xi. So now I actually write out my sum. It's m1x1 plus m2x2. I have reached the maximum number of things in my system, so I'm done with my summation. So I now plug in all of my numbers. Might help if I could actually write down the numbers correctly. I'm just going to move this over so I have a little bit more room. It's 1 over the total mass, 6.0535 times 10 to the 24 times the mass of my first object. I'll call that Earth. $5.98 times 10 to the 24 times the x-coordinate of Earth, which I've called 0, plus the mass of the Moon, 7.35 times 10 to the 22, times the position of the Moon, 3.84 times 10 to the 8th. And that is, when I plug in all of those numbers, is going to give me my center of mass. Note that this first term is 0, because any number times 0 is 0. So it's just 1 divided by that total mass times 7.35 times 10 to the 22 times 3.84 times 10 to the 8th. And assuming I haven't made a calculator error, this gives me a center of mass of, let's see, 4.66 times 10 to the 36. Now that's not very far. That's not a very big number. This is about 100 times smaller than this number, which implies that my center of mass is actually somewhere kind of over here in that ballpark. And this is actually true. The diagram I have here uses slightly different values, but it is a good illustration of this nonetheless. Like I said, this uses slightly different values for things like the distance and the moon and so on. So ignore the fact that this number is slightly different. The number that we got was, I think, 4.66. And we see that the center of mass of this system is, in fact, much closer to Earth than the moon. And that's because of how much smaller the moon is. In fact, the center of mass of this system is in the Earth. This actually leads to another source of wobble because, fun fact, the moon doesn't actually orbit the Earth. It's actually that both the Earth and the moon orbit the center of mass of the system. So this actually means that the Earth wobbles a little bit as the moon orbits it. Same thing with the sun and the Earth. Okay, there's a one-dimensional example of how to calculate a center of mass. Now let's move on to two-dimensional objects. Now it turns out when you have, say, two-dimensional systems, here I have a few popsicle sticks that has, note these have x positions and they have y positions. Turns out when you have an object in the y direction, you can calculate its y component of its center of mass using the same formula, you just use y instead. This similarly simplifies for the case of two objects. Now, the one thing I want to say is that for two-dimensional objects like, say, for example, popsicle sticks or metal rods, we can actually always assume, assuming these objects are nice and well-behaved and uniform, that their center of mass is in their center. This is a result that we've already come across. And so in this particular diagram that I have down here, you would imagine that basically I have three popsicle sticks. Each has a mass that is concentrated at its center, like so, and then I would use my formulae to combine those 3 points. And that's actually what we're going to do right here in a two-dimensional example. Now, we have three popsicle sticks. Each have a length of 8 centimeters with equal mass m that are arranged in this U shape. We want to know what the xy coordinate of the system's center of mass is. So the first thing I want to do in problems like this is I want to label, using coordinates, the masses in question. So for example, here I have a mass that is located at the x-coordinate 0, the y-coordinate 4 centimeters. Note that it is 4 because these objects are 8 centimeters long, and the center of mass will be at the middle of that object. So 8 divided by 2 is 4. Similarly, I have another mass m here that is at x-coordinate 4, y-coordinate 0. And finally, I have this mass, which is at x-coordinate 8, y-coordinate 4. So, at this point, what I'm going to want to do is calculate the x center of mass is 1 over the total mass times the sum of mi xi for I going from 1 to 3. 3 because there are 3 popsicle sticks. And then I will also do the exact same thing for y. 1 over m tot, sum of mi yi from 1 to 3. At this point, if you were doing this on your own, even if you managed to set it up this far, you might run into trouble here, because it is at this point that you'll notice we are not told what m is. This is very similar to the case we went through back here. When all objects have the same mass, or the masses are related to one another using a formula. Maybe I tell you one object is twice the mass of another. What we'll see more often than not is that unknown mass will cancel out. And so we're going to proceed with this problem under the hope that that will do so. So our first step is always to find the total mass. That's the mass of the first one plus the mass of the second one plus the mass of the third one, which just gives me 3m. And so from there, I just do my sums. Center of mass in the x component is 1 over the total, 3m, times the sum of m times x1 plus m times x2 plus m times x3. And note that I can factor a mass term out of each of these. So I can pull that term common. I am left with m over 3m, x1 plus x2 plus x3. That allows me to cancel out those masses, and I'm just left with 1 over 3 times the x-coordinate of my first object, which I just read off my diagram, 0. The x-coordinate of my second object, 4. The x-coordinate of my third object, 8. 0 plus 4 plus 8. That is going to give me 1/3 of 12, which is, of course, 4. I perform the same general operation for my y component, y center of mass. We're going to see that this becomes 1 over 3m, m times y1 plus m times y2 plus m times y3. Just as we saw before, the unknown mass is going to cancel. I'm going to be left with 1/3 times the y coordinate of my first object, 4. Again, I'm just reading this off the diagram. First one is 4, second one is 0, third one is 4. So it's 4, plus 0 plus 4. That is 8/3. And this, we can represent this, numerically with some decimal points as just 2.67 centimeters. Sorry, I'm in the way. There we go. So note that we could take these coordinates and we could plot them on our axis. This is the line that coincides with x equals 4. And we'll call this line the one that corresponds to y equals 2.37. So this is the center of mass, and it is at the coordinate 4, 8/3. And that might be confusing. 4, 2.67. And really, this is, as complicated as it gets. I could maybe make this problem more complicated by, say, giving you 3 different lengths of, popsicle sticks. If I was really being cruel, maybe what I'd do is I would tell you, I have one popsicle stick of length 4 and mass m. I have one that is length 8, mass 2m, and a third that is length 12, mass 3m, maybe something like that. And I could ask you to find the center of mass, but the process would be the same. You know, this would be at 0, 2. This would be at, what, 4, 0. This would be at 8, 6, and you would just repeat the process. You'll get some practice with this, I think, on the homework. Other than that, we just have one more topic to talk about, which is how this works when objects are in motion. Now, when objects are moving, you can still describe their center of mass. But of course, that center of mass is going to change with time. I can quantify how much the center of mass has moved. So this is the displacement of the center of mass, by performing the same sum that I normally do, except instead of plugging in the coordinates, I plug in the change in position for each individual object. So this is the displacement of object 1, the displacement of object 2, the displacement of object n, and so on. So you note that this really doesn't change my formula very much. The only difference is, instead of this being an x coordinate, this is now a change of that individual object's position. Now, this is useful because if this is a displacement, then we can calculate the average velocity of the center of mass by taking this displacement and just dividing it by time. If we divide this formula by time, note that we get this delta t can we just be pulled into the sum here, and this looks like the average velocity for each individual object. So the velocity of the center of mass is just 1 over the total mass times the sum of the mass of each object times its individual average velocity. You'll note that this number in here represents the object's average momentum. You might just see that being mv. But note that the result is a velocity because we take a momentum and then we divide it by mass. Just to give you a little quick idea of how this might look, here are two objects, or two train cars. Trains. And I can calculate their center of mass, assuming they're equal mass. It'll just be in the middle. So there is the center of mass here. But now, the train that's out front, you'll notice from its velocity vector, it's smaller than this one. So this one's going to be moving more slowly. So when I advance time, PowerPoint, why do you forsake me? When I advance time. This train moves forward only a very little, but this train moves forward a lot. I can then recalculate the new center of mass. Note that it has moved forward. If I continue this process for, say, 3 different cases, and I just calculate the center of mass each time, you'll note that the center of mass is actually moving a little bit differently than the 2 individual train cars. The center of mass will move faster than this one, but slower than that one. And we could calculate that using this formula down here. Finally, we can also calculate, like I said, the momentum associated with the center of mass. We just take that center of mass velocity and we multiply it by the total mass, and that gives us the momentum associated with the system. Note that if we just took away these subscripts, this would just be momentum equals mv, and that's why we're able to do things like, say, a car has a momentum mv. Yeah, a car has a lot of parts, but what we're doing is we are implicitly assuming that we're talking about the velocity of the center of mass multiplied by the total mass of the object. Fun fact, we can also apply Newton's second law using the impulse momentum theorem to talk about the net effect of forces on the total object and talk about the acceleration of its center of mass. Turns out all of the physics we've been doing, we just assume that these are net effects acting on the center of mass of objects, and nothing changes from what we've done so far. So the center of mass of a system behaves as though all of the mass of that system were concentrated at the center of mass, and as if all of the external forces act on that central point. And that's it. We're done with Chapter 7. 5 minutes early today, even. We're done with Chapter 7. Next week, we will start on Chapter 8 on Monday. We will do the exam on Wednesday. We will continue with Chapter 8. Then we will transition to Chapter 10. Then we will have our exam for Chapter 4 on, I think, November 13th, I think. Yeah, November 13th. And then we'll basically be in the home stretch, folks. So let me know if you have any trouble. My walk-in office hours are open as usual today, starting at 11. And I have limited availability in the afternoon, although that might have filled up since the last time I looked. Otherwise, like I said, I'm going to be expanding my office hours on Monday and Tuesday if you'd like to meet prior to the exam. So until then, folks, good luck with all of your work and enjoy the rest of your week. And I hope you have a great weekend if I don't see you before Monday. Bye-bye.